Hello everyone, welcome to our discussion of horizontal motion and falling. Today we're going to talk about the effect of moving sideways, so horizontal motion, on the falling of an object. Let's get started. So the question we're trying to answer here is, how does horizontal motion affect falling? And we saw in the lab already that how fast you're moving sideways doesn't affect how fast you move down, so the time it takes to hit the ground. What we did is we slid that heavy washer across the table, and as that sliding washer went off the table, it barely nicked a second washer that was sitting here on the edge. That washer on the edge just fell straight down to the ground as the other washer slid and flew way out over here. And what we saw with our video and our eyes and our ears, we observed that the washer hit the ground at the same time. So that sideways motion does not mean it takes longer for this washer to hit the ground. It takes the same time as the other one. So it seems like these two motions, the horizontal motion and the vertical motion, are separate, but they add together to create the overall motion. So today we're going to take a look at how to separate them and add them together. Think of them as separate and add them together to find the actual path of something. We'll start here with a ball rolling along the table, and let's give it a velocity of 200 centimeters per second. And we'll take a look at this ball where it's at every tenth of a second after leaving the table. Okay, and we'll first think about it, well, what if there wasn't gravity and it was just moving horizontally? Where would it be? And also we'd look at, okay, so what if it wasn't moving and it just fell? And what we're trying to say is the combination of those two, of the just falling and just horizontal, is its actual motion where it is moving horizontally and falling at the same time. So let's do that real quick. So as it leaves the table here, a tenth of a second later, it's going to have gone 20 centimeters. So it will be right here. And another tenth of a second later, it will be 20 more centimeters away, here and here. Remember, this is if there was no vertical stuff going on. So if it wasn't falling, it would just follow this path all the way across. That should be enough. It'll keep going, right? Now, what if it were to fall without moving sideways? So we're looking at, this was its horizontal motion. And now let's see what happened with this vertical motion. If we just let it fall here, so we start here, we let it fall straight down. So to figure out how far it will be from its starting point, we need to use some math, right, here. And so now delta H, change in height, is equal to 1/2 AT squared, right? So this is our equation that tells us how far we fall from our starting point. Now, 1/2 A, in this case, we're using centimeters. So we're going to have to convert. We know that A is normally -10 meters per second, but we're going to need to convert A into centimeters, and that's going to end up being 100 times more. So it's going to be -1000 centimeters per second. So this is the A we'll use in this equation because we're using centimeters. So now we have here that the change in height is equal to 1/2. Let me go back and put the numbers in there. 1/2 times 1,000, -1,000, is -500 centimeters per second times t squared. So now we can use this equation to figure out the height at each of these different times. And again, we're looking at every tenth of a second here, not full seconds. So when we plug in 0.1 into this equation, the answer we end up with is -5 centimeters. And we put in 0.2, we get -20 centimeters. Then we get -45 centimeters. Then we get -80 centimeters. And finally, if you plug in 0.5 into here, square it, multiply it by this, you get -125 centimeters. And of course, all those negative changes in height mean that we're losing height, that we're falling. So let's plot these. So this ball, if it wasn't moving sideways, would fall straight down to the 5 centimeter mark, right about yay. And then at 20 centimeters, or 0.2 seconds, it would be at -20 centimeters, which would be about here. At 0.3 seconds, it would be at -45 centimeters, which is about here. And then at 80, about here. And then about 125, which is about here. So this ball is doing two things at the same time. It is moving sideways and it is falling. Its sideways motion is this, here, 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 and here, while its falling motion is here, 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 and here. Now to find out where it actually is, we just add these two vectors together. Here's a distance vector, here's a distance vector. Their sum is the diagonal. It's the one that's straight across from here and straight down from here. And this is where the ball actually is. Over 20 centimeters, down 5 centimeters. At the 0.2 seconds, we are over 40 centimeters and down, we've fallen 20 centimeters. At the next one, at 0.3, we've gone over 60 centimeters in 0.3 seconds and we've fallen down 45. So we're here. And the next one at 0.4 seconds, we've gone over 80 centimeters and we've fallen down 80 centimeters. And on the next one, we've gone over 100 centimeters and fallen down 125 centimeters. That is the actual path of the ball. So it leaves here and follows this path. And this path, of course, is a curved path. Just like that. Well, what if we had a ball that was traveling faster? So let's switch over and do, I don't know, blue will be fun. And we have this ball here. And as it goes off, it's actually traveling at a velocity, a much larger velocity of 500 centimeters per second. So in 0.1 seconds, it actually gets out to 50 centimeters. So it would be here. And then it gets out to 100 centimeters. It would be here. And then 150. And then 200. And then 250. So this is its sideways motion. If it weren't falling, it would do this. If it was falling, it would do the exact same thing as the red one. It would fall straight down 5, 20, 45, 80, 125. So those are already plotted. So to figure out where the blue one actually got to, all we have to do is we know if it's going this fast, it's going to go sideways 50 centimeters, and it's going to fall 5. Just like everything else falls 5 centimeters in 0.1 seconds. And then if we go over here and we go 0.2 seconds, it's gone 100 over, and now it's fallen 20. Just like everything else falls 20 centimeters in 0.1 seconds. Over here, down to 45. And then here from 200 all the way down to 80. And then here, all the way down to 125. So the faster we travel, we don't fall any faster. We're still following 5 centimeters in the first 0.1 seconds, but we do move farther sideways as we fall. So this blue one would follow roughly this path right there. Okay. So notice at every 1/10 of a second, these are directly across from each other. And I've got some video I want to show you this in reality of how they stay side by side as they fall. Even though one is moving faster sideways, it doesn't affect how it falls. Okay, so what we have here is a great video of exactly what we're talking about. So what this contraption does is there's this metal rod in the middle here that when he pulls the lever, this metal rod's going to shoot this way. That will knock this ball off while releasing this ball, and it'll happen at roughly the same time, and we can watch this in slow motion. So as we go, he's pulling the lever up, and the rod's moving, it's knocked that ball off, and it's about to release the other ball right there. So you can see they release at roughly the same time. This one released a little bit early, but as it falls, watch what happens. So as they fall, even though this one's moving sideways, and this one's going straight down, they're at the same height the entire time. Same height, same height, same height. And sure enough, they hit the ground, bam, right there, same time. Yeah? And even watch this, even on the bounces, even though it's still moving and it's bounced, they're still at the same height each second. They get back up to the same height, back down. Bam, hit bounce again. same height, all the way off. Yeah? So it's a great example of what we've been talking about, that sideways motion doesn't affect the vertical motion. So our conclusion today, two-part, is that first, horizontal motion does not affect falling. So if you're moving sideways, that won't change how you fall. You fall the same no matter what. So then also the time it takes an object to fall depends on only the height it's dropped from, not any kind of sideways motion. And the equation for falling time, how long it takes to fall from a certain height, is given by the following. So we know this equation. I'll do it in blue. So delta H is equal to 1/2 AT squared. Now to know what time, we're looking for time, how long it takes, we've got to solve this equation for time. Of course, to do that, we multiply both sides by 2 to get rid of the 1/2. So we get 2 times delta H is equal to AT squared. To get rid of the times A and get T by itself, we divide by A on this side, divide by A on this side. We get here that T squared is equal to 2 times the change in height, how far you fall, right? So this is how far you fall, divided by the acceleration. And then finally get T, we just take the square root of both sides to find that T is equal to the square root of 2 times the change in height, how far you fall, divided by the acceleration due to gravity, which is negative 10 meters per second on worksheets and stuff, and negative 9.81 in reality when we're doing lab work. So this is our equation for how long it takes for something to hit the ground if it falls this far and gravity is negative 10. Awesome. That does it for our conversation today. It's been fun. I hope you enjoyed it, and we'll see you soon.